Hi, this is going to be our third review session. This is for exam 3. That's going to cover chapter 19 and 20 of Brown, LeMay, and Barston book. And let me go over some of the sample problems so that you understand how to do problems like those. So our first practice problem, okay, I have delta H value of minus 200 kilojoule. Delta S value is given 5,000 joule, and temperature is 60 degree Kelvin. The question is, this is coming from a reaction. Will this reaction happen spontaneously? So our first question is, will this reaction happen spontaneously? What that means is, if I have these temperatures, if I don't do anything, will this reaction go on? If it is yes, then obviously we know that this temperature, delta G, is going to be negative. So by looking at delta G value, we can tell whether a reaction is spontaneous or not. If delta G is called free energy function, change in free energy from reactants to products, if that is negative, that means reaction is going to happen spontaneously. If it is positive, that means it's not going to happen spontaneously. So let's check in this case. So delta G, so in exam, if I ask you a question by giving these kind of values, whether a reaction is spontaneous or not, you'll have to do this little calculation. Delta G is given by delta H minus T delta S. You need to be careful about the unit. Here the delta S unit is in joule, and this is in kilojoule. So divide this by 1,000 to get in kilojoule. So I'll write it down as minus 5 kilojoule. Let's assume that I have two more significant figures, 5.00, and this is 200 point. That's three significant figures. So now let's plug in these numbers. 200, that's kilojoule, minus T is 60, that's Kelvin, and delta S is given, and now let's write down in kilojoule, minus 5.00, and this is kilojoule per Kelvin, because this is S, or entropy. Entropy unit is kilojoule per Kelvin, so this is kilojoule per Kelvin. So Kelvin would cancel out, so I have kilojoule, and so I have plus 300 here, minus 200 here, so it's going to be plus 100 kilojoule. Since delta G value is positive, not negative, it's non-spontaneous. So in exam, when we give you these values and ask you to predict whether the reaction is going to be spontaneous or not, you should calculate delta G value. If that delta G is negative, it is spontaneous. If it is positive, it's non-spontaneous. We often add another question to this. Let's call it practice problem 1A. And practice problem 1B, the question is, if it is non-spontaneous, at what temperature will it be? So if it is non-spontaneous, then at what temperature it will be spontaneous? So obviously it's non-spontaneous at 60, so now we need to find out at what temperature it's going to be spontaneous. That means we need to find out at what temperature delta G becomes just negative. So let me show you how to do it. Since we are going to find out the temperature, obviously we would not be using 60 anymore, but the other numbers are all right. So we can still write down the same expression, delta G is delta H minus T delta S. So delta G, we'll have to get it negative, minus 200, this is kilojoule, minus T, we don't know this value yet, so let's write down T. Delta S, we know it's minus 5 kilojoule. So this is going to be kilojoules, so both are kilojoule per Kelvin, and this has Kelvin. So kilojoule and kilojoule. Now, normally you'd think, if I keep on increasing temperature until these two numbers are same, then delta G is going to be 0. So that means if I set this equal to 0 and solve it, this is going to be plus, because it's minus and minus, this is plus 5.00 T. So that means T is going to be given by, this is, if you go to bring this 200 on the other side, it's going to be plus 200. So 200 divided by 5.00. So in this case, I get 40.0 Kelvin. Now let me explain to you what's going on here. If I have exactly 40 here, you can double check. I'd be getting equal to 0, not minus. But if it's more than 40, then this number is going to exceed. This number is going to exceed 200. I'm sorry, if it's more than 40, then we're going to have this number exceeding this, and then it's going to be positive. If it's less than 40, then it's going to be negative. So your answer to this question is temperature has to be less than 40.0 Kelvin. So you be careful in getting these kind of numbers. First we set it equal to 0 to find out at what temperature they just balance each other. That means at what temperature this is going to be equal to 0. But we want negative. So this number has to be smaller than 200, because this is positive, this is negative. And in order to get less than 200, this T value has to be less than 40. You can try these. For every T value less than 40, this delta G is going to be negative. So that's why answer is at temperature lower than 40 degree Kelvin, this reaction is going to be spontaneous. Let's now go over second practice problem. We'll be showing you a calculation of change in entropy in a chemical reaction. Calculation of delta S, or change in entropy in a chemical reaction. As an example, I can show you a simple reaction. 2H2 gas plus oxygen giving 2H2O gas, and I copied these values from back of the book. Appendix has all these values. In exam, I'll give you these values, or you can get the data table. So if I want to write down, before I do this calculation, let me just copy the values. 130.88. These are all in joule per mole per Kelvin. 205 joule per Kelvin mole, and this value is 188.83. 188.83 joule per Kelvin per mole. Now something I need to caution you is all the values that we gave are for per mole. But look at this. This have 2 moles. This has 1 mole. This has 2 moles. So accordingly, you have to take into account those number of moles. So delta is 0, change in entropy as you go from product to reactant. The superscript 0 stands for standard state. Standard state means under the room temperature, 1 atmospheric pressure, and so basically pressures at 1 atmosphere, and also if you're dealing with a solution, it will be 1 molar solutions. That's the standard states. So this is going to be S0 for all the products minus S0 for all the reactants. In this case, I have water as products and I have 2 moles. So I need to multiply this number by 2. So it will be 2 times 188.83. So this is going to be joule per Kelvin. I already got rid of mole because you have 2 mole here and you had a per mole at the bottom. The mole would cancel out. So now onwards, I'm not going to write down these moles because they are cancel out. Minus the reactants. We have 2 reactants. 2 times S0 for hydrogen minus 1 times S0 for oxygen. Now, we already know these values, so let me write down here 2 times 188.83 minus 2 times the value for hydrogen, 130.88, and then for oxygen value is 1 times the same as that value, 205.0. And these are all in joule per Kelvin unit. So I'm just going to write down the final answer, and you should make sure to double check whether my numbers are right. Minus 88.5 joule per Kelvin. That's the final answer. So what we see is delta S value or entropy has decreased as you go from reaction to the product. Sometimes we miscalculate, and it's a good idea to check whether it makes sense, whether the answer makes sense. I got a negative number. That tells me that entropy is decreased as I go from reactants to the products. Does it make sense? So let me write down here entropy and randomness. Just to give you some understanding, without doing the math, whether we can understand that this, in this case, entropy is expected to decrease. So entropy or randomness can be influenced by number. So randomness and number, let's write down here, randomness and number. And second factor is randomness and volume. Volume or free space. Randomness and number. Think about, this is a room where I have 5 kids running around. Okay, these are 1, 2, 3, 4, 5. They're running around. And I'm looking for one particular kid. Now, when the five kids are running around, it's a little bit harder for me to track down one kid if I compare it with a room where we had only one kid running around. So in other words, randomness is increased here because of the larger number, because it's harder for me to pick that kid that I'm looking for. When only one kid is there in a room, that means much easier. I can just say for sure that that's the person I'm looking for. Now in this case, 5 out of 5. If I have instead of 5, I may have 100. That means as I increase the number, randomness is increased. It's much harder for me to track down a particular kid. Same thing is true for a chemical reaction. As the number is increased, randomness is increased. because that person can hide anywhere in this area. Now let's come back here now. What happened with the number here? We started with 2 hydrogen and 1 oxygen, 3 at the beginning. As we get products, the number has decreased. So when number has decreased, so if I look at initial entropy and final entropy, or final randomness, entropy is the same as randomness, the final randomness is less because I have a smaller number, fewer molecules. Initial is more. So basically delta S would be given by final minus initial. Since final has a smaller value, when you subtract, it's going to give you a negative number. So that means it does make sense that we got a negative number, because as we get products, the number has decreased. So anytime in a reaction, if you find that a number has decreased, you'd expect a decreased entropy or randomness, provided they're all gases in this case. You can't have a solid and gas mixed together, and because solid, we'll have to treat differently. So we'll come back to that at a later time. Now randomness and volume. Let's assume that I have one kid in a room. It's much easier to find him in that room. If I say that this kid is in a much bigger space, somewhere in a state college or Dubai, it's much harder to find him because the volume is now increased, so randomness has increased, because that kid could be anywhere in that area or somewhere in the country. That's even give you a much bigger volume and it's much harder to find. So randomness also increases with the volume or area where one can freely move around. So keep that in mind with the 2 important factors in entropy and randomness and how they can change. There are other factors too, like if you add heat, randomness is going to increase because these molecules would have greater energy, they would be moving faster back and forth. So those conditions are also important. So at this point, I think we're ready to do the 3rd practice problem. So this is practice problem 3 for exam 3. The question would be like this. I'll give you one sample example, like calculation of delta G, change in free energy at 298 Kelvin, that's room temperature, for this reaction, 2H2 plus O2 giving 2H2O. And these are all gases. Okay. Now the hydrogen is under pressure of 2 atmosphere, oxygen 1 atmosphere, and H2O 2 atmosphere. Okay, so these are the pressures of hydrogen, oxygen, and H2O. Free energy of formation. You get these from back of the book. So in exam, obviously you should be looking at these tables. Free energy of formation for H2O, let's write down the values first, is minus 228.57. 57 kilojoule per mole. Delta GF0 for hydrogen. For H2, delta GF0 for O2, they're all equal to 0. I want you to know that for pure elements under standard states, free energy formation is equal to 0. That's on that basis we calculate the other free energies. So this is a pure element. Under standard state, this is a gas, this is also gas, and the value is 0. So this will save you time if you know ahead of time that how to get other values. Okay, now we have all these delta G values given, and now we need to calculate delta G at 298 if it's not under standard state. And truly you can see that these are not standard states. Under standard state, it should have 1 atmospheric pressure. Now you see that this has 2 atmospheric pressure, this has 2. That means I cannot calculate delta G unless I apply this expression. Delta G equals to delta G 0 plus RT log of Q. That's the natural log of Q. This is the standard state value. Delta G0 is the standard state value. So you get it by using, you can get it by using these values, free energy, standard free energy values. So let's first do this part of the calculation before we do the other. Okay, in order to do this calculation, delta G0, I'm talking about this, will be given by free energy of products. Now I have 2 times of this free energy, 2 times, let's first write down the expression, delta GF0 for H2O. Now why 2 times? Because there are 2 moles of H2O. And this is the value that I got from back of the book, minus the values for hydrogen, which is 0, minus the values for oxygen. So it would be 2 times the value for hydrogen, 1 time value for oxygen. They're all zeros. So now it's going to be 2 times this value minus 228.57. That's going to be kilojoule because 2 is mole. So it's going to be, let me just write down the final value, minus 457.14 kilojoule. So minus 457.14 kilojoule. That's the delta G value. So how do I get that value? These are pretty straightforward. By looking at the values from back of the book, you get these values, and these are the standard free energy change values for each compound. The product first minus the reactants, and that gives you minus 457.14. So we're going to use that value here. So let's write down here, minus 457.4, that's kilojoule, plus, now this contribution is coming from the fact it's not under standard state. So we'll have to account for that, how it's going to be different. So let's now put down R and T values there. R is 8.314 joule per Kelvin per mole. This is the constant, R value. This is the ideal gas constant. Now keep in mind, ideal gas constant have 2 values. One is 0.0821 liter atmosphere per degree Kelvin per mole. But in this case, it's not the liter atmosphere unit. You need joule unit because you're getting energy unit. So that's why it's the joule per Kelvin per mole times the temperature. So temperature has to be given, and we gave you that temperature, 298 Kelvin. So 298 Kelvin, that's T, that's 298. Now you'd have to log of Q. The Q is defined like equilibrium constant, except those are not equilibrium values. So let's write down first the expression. Pressure, partial pressure of H2O, partial pressure of H2O raised to the power 2, because coefficient is 2 here, divide by partial pressure of hydrogen raised to the power 2, the coefficient becomes power, partial pressure of oxygen raised to the power 1, because this has 1. So like this is 2, 1, 2. And that's why you have something like this. Now, here I have a mismatch of unit. This is in kilojoule, this is in joule. So make sure you divide by 1,000 to get in kilojoule before you get the final answer. So don't forget to do that. So let's put down under 1,000 underneath and change this joule to kilojoule. 1,000, that makes kilojoule. Now every unit is in line. Now this Kelvin would cancel out. The whole thing would be calculated now per mole. We took care of this. Now if you do this math, by the way, these values are already given. This value is for H2O is 2.00 squared. 00, that is squared. And this value for hydrogen value, you're going to use 2.0 squared, and this is 1.0. So basically this is the given values. And doing this math, this is what you're going to get. Minus 457. 57.14. Now the interesting thing is, I must tell you, the way we took these values, the top value is 4, bottom value is 4, because this is 4 times 1, so it's a log of 1. So this term becomes 0. So we selected our pressure in such a way that there is no contribution coming from here. So our value of delta G is same as value of delta G0, and the unit is in kilojoule. But it's not going to be the case in every situation. I selected those values in such a way that that term doesn't, that term disappears. Now we're going to do practice problem 4. Now in this particular problem, an electrochemical equation is given. So let me first write down that. Zinc plus nickel 2 plus in aqueous solution, because zinc is solid, aqueous solution, giving zinc 2 plus in aqueous solution. Aqueous solution is water solution plus nickel, which is a solid. The questions are cell voltage or cell EMF. Cell voltage is same as EMF, electromotive force, under standard state. What is cell EMF or cell voltage under standard states? Okay, so that's the question. Under standard states, what will be the values? Part B, cell EMF or voltage, when we have following concentrations of nickel and zinc. When nickel concentration, let's write down the given values, nickel 2 plus concentration equals to 3.00 molar, and zinc concentration equals to 0.100. Okay, so this is an equation, electrochemical equation is given, and from here we can need to find out cell voltage or cell EMF under standard states. Under standard states means 25 degrees centigrade, 1 molar concentration of these ions in the solution, And if that is the case, let's see what we get as cell EMF or cell voltage. First, you need to split this reaction into two halves. I think that's something that we need to do based on similarity. Zinc 2 plus. So that would make 1/2 reaction. In balancing of this kind of reactions, you first balance elements other than hydrogen and oxygen. So in this case, zinc. So zinc 2 plus, the number of zinc is same on both sides. So I'm done with that part. There is no hydrogen or oxygen to balance. Now, you move to the charges. There is no charge on left hand side, there is +2 on this side. So that means I need 2 electrons. So now it's balanced. Now my other half cell reaction would be nickel 2 plus aqueous solution giving nickel solid. Again here nickel is balanced. I have same number of nickel on both sides, but this is +2, but this is 0. So I need 2 electrons. So now it's balanced. Make sure that in 2 half reactions you have the same number of electrons. This gives up electron, this absorbs electron. I mean that's how electrochemical reaction takes place. 1/2 cell reaction is going to provide electron, the other half cell reaction is to consume electron. So make sure you understand that. So if these two numbers are not same, you'll have to make it same. During balancing of electrochemical reaction, I'll show you that how we can balance the electrons. This is a simple half cell reaction. The more complicated ones, we'll show you how this balancing is done, which would be the next problem. Okay, now these are the 2 half reactions, and we'll have to have a standard cell voltage for each half cell reaction. In other words, I need to know E0, this is oxidation part, and zinc becoming zinc 2 plus. I often write down like this, and that value needs to be known. And this is reduction value, where nickel 2 plus is changed to nickel, and that value also you need to know. So I suggest that you can get those values from back of the book. I got those values, but you can always double check. This oxidation is 0.763 volt. Keep in mind, book only lists reduction potentials. That means zinc 2 plus to zinc, and that would have a negative number. In order to convert from reduction to oxidation, you need to change the sign. So I changed from minus 0.763 to plus, because I'm writing down oxidation, not reduction, because this is an oxidation reaction. In this case, you can keep the number as well as sign intact, because that's how book would list those values, and that value is minus 0.28. 0.28 volts, that's minus. Now if you add these two reactions and add those two values, you get E0 cell, a standard cell voltage, or EMF. Would be sum of these two numbers, 0.763 minus 0.28, so I'm just going to copy a number here to save our time, 0.483. So that's the EMF or cell voltage under standard state. Now we're going to calculate under non-standard state. This is the non-standard state. 3 molar nickel, 0.1 molar zinc. It's not 1 and 1. So that's why we need to be careful about how to do this. Now, in order to do the second part, we need to use this expression that I used before, which is coming from E cell. You can derive it from delta G equals to delta G0 minus RTNF by log of Q. But if you do the math, you're going to get this. E cell, E0 cell, E cell equals to E0 cell minus 0.0592 over n log of Q. This is now not natural log, it's a log with respect to base 10. Now either cell, we already calculated that. I think I erased that. So I'm just going to copy that number here, 0.483. So this is 0.483 minus 0.0592. You can write down this expression as long as temperature is 298 Kelvin. And n value is how many moles of electrons being transferred from this cell to this cell, one half cell to the other cell. Transfer of 2 moles of electrons had happened. So n equals to 2. So this is 2. Log of Q, the product values on the top, reactant values on the bottom. Let's quickly get this product. Add up these two. So solid, we'd have a zinc solid plus nickel 2 plus aqueous, giving nickel solid plus zinc 2 plus aqueous. And 2 electrons would cancel out. This is on the right side, this is on the left side. Now, this is the heterogeneous equilibrium. So I'm going to ignore these 2 solids. So I'm only going to write down zinc concentration on the top and nickel concentration on the bottom. Because this is product, that's the reactant. Nickel 2 plus on the reactant side. These are all raised to the power 1 because this is all 1 and 1 reaction. Okay, now let's plug in these numbers. Zinc 2 plus, they gave you this value to be 0.100 molar. Nickel 2 plus, 3.00. Okay. Now if you plug in all these numbers and do the math, your final answer is going to be, this is what I found out, 0.527. 527 volt. So the answer to this part B question, this is for part B. When the nickel concentration is 3, zinc concentration is 0.100, then the voltage becomes 0.527. So make sure you know both ways of doing this kind of calculation. So the first step is you split the reaction into 2 half reactions, then balance it, and then do the standard EMF calculation from oxidation value as well as reduction value that you get from back of the book. I just want to caution you, back of the book has this value, E0 reduction, zinc 2 plus, that becomes zinc, and that value is minus 0.763. But we had to convert that to zinc 2 plus, oxidation. And that's why the sign got changed, the number remained the same. When you add these 2 numbers, oxidation, this is anodic reaction, this is anode, where oxidation takes place. This is cathodic reaction, where reduction takes place. And I told you that this number of electrons has to be same. So in our next problem of balancing, we are going to show you how we can balance not only just elements, we can also balance number of electrons. I'll give you introduction to those balancing before we do the problem. Those reactions are going to be a little bit more complicated than this. It should have hydrogen as well as oxygen. So first you need to balance elements other than hydrogen and oxygen. Then you balance oxygen by adding H2O. Then you balance hydrogen by adding H pluses. And at the end, you balance each half reaction by adding electron. So in our next problem, we'll go over that.